Let me start by saying that science denial creates very good job security for analytical chemists. Because it's almost like there's a molecule of the month that's going to keep us employed. BPA, I mean, that's the molecule of the past how many years? I don't know. But, but just the other day on the news, morning news came on, and they were talking about 1,4-dioxane in consumer products, which is basically a dimer of ethylene oxide and ethoxylates that are used to make detergents and surfactants and everything like that. It's inevitable that you're going to get a little tiny bit of dioxane in it. So the next day when I came to work, immediately I bought a deuterated internal standard of 1,4-dioxane because the phone's going to be ringing off the hook, emails coming in, so we need to focus on whatever molecule is important at that minute. So thank you for the introduction, Greg, describing, the subject matter that we're going to discuss today. Right now we have global regulations that mandate food packaging migration testing. We also have to deal with, for instance, state regulations like California Prop 65, which people have been discussing this morning. The regulations are not necessarily all harmonized, so it makes it challenging. I'm going to focus pretty much today on FDA regulations in the United States, but we do, right now, global migration testing, to cover pretty much a global marketplace. Did that just change by itself, or?
I don't know, it might be the electricity. It shouldn't.
Okay. In any event, if I just go back, let me see if I can go backwards. Here we go. One thing I want to mention is that there's guidance documents in all of these regulations. And the guidance documents, they outline very accurately how to conduct the tests, but they don't give any examples of analytical methodology to achieve the goals of the testing, aside from what we call gravimetric end tests, which are just measuring total extractable residue, non-volatile residue on evaporation. But otherwise, when you're looking for migrants and the different analytical techniques that are used, they're really not detailed in any of these regulations. So that's a challenge. Now, when we do migration testing, I really consider, aside from gravimetric testing, two different types of migration testing. One of them is targeted migration testing. That's where you have specific target analytes and you have validated analytical methodology to analyze for those target compounds. So an example would be like Greg Pache with his master's research. He worked on chloropropanols in paperboard, where they're using wet strength resins in paperboard that have epichlorohydrin as one of the precursors in the polymers, and they can hydrolyze and form chloropropanols. So we have very specific methods to target chloropropanols for analysis, extremely sensitive and low limits of detection. Another example would be like BPA. Everybody's talking about BPA. People want to know, is there BPA in the sample? And they want sub-part per million detection limits. They give me recycled feedstocks, like recycled PET or whatever, product. And they want to know, does there BPA? And is it sub-ppb levels, So again, that is, I don't know why it keeps changing by itself, trying to keep me on time, I guess.
Yeah.
All right, so that's, you did that, Greg, right? Okay.
Just so you all know, I do have another one here.
Right. Then we have what we call screening studies, and that's what I'm going to talk about today. Now, most of the samples that come into the lab for analysis are submitted by industry or food companies, and they don't know what's in the packaging. Even if the generic description of the packaging is given, all of the ingredients in it are proprietary. There's inks, printing inks, and the ink companies don't disclose the ingredients. Adhesives, right? We have one of my colleagues here from an adhesive company, Joe Sminato. The resins that they blow films from, they have additives in them. It's all proprietary. Very hard to get the information from the manufacturers. But our challenge is to do migration testing and, figure out what's coming into the food chain. So, what are the requirements for screening? Well, you need rapid techniques. People want data fast. They have to make decisions on the data. I have customers that do a production run and they want to release it to a client, but the client wants migration testing first to make sure it meets their specifications. So literally, you're holding up shipment waiting for results. And one of the things that takes the longest when you're doing this type of testing is often there's a 10-day incubation, which is, almost 2 weeks. So you have to set the samples up, do the incubation. At the end of incubation, analyze them, process the data, and get reports out, quickly to the clients. They have to be low cost as well. If the cost is too high, customers won't do the testing, or they'll cut back on the testing, or they'll try to use shortcuts to get the data. So you have to keep costs down. And really very important for screening is that the analytical methodology that you use must capture the widest scope of migratory species using the minimum resources invested in the analytical work. And of course, the data has to be accurate, precise, and reliable. So, I'm going to explain the generic screening migration test protocol. Basically, it starts with food site extraction in migration cells or in the containers themselves. So if customers give like drinking cups or plastic tubs like you would fill with butter or margarine or something like that, very often we could do the testing in the container itself. But there's limits on temperature, like you can't put liquid food simulants into containers and heat them above certain temperatures or the solvent will evaporate and you'll lose your solvent. So the next thing is we have to choose a food simulant. And the most common food simulants we use are ethanolic solutions like 10, 20, 50, 95% ethanol. We sometimes use isooctane as a fatty food simulant. 3% acetic acid, which is really an EU food simulant, and also, China actually uses 4% acetic acid, and we use that for acidic food simulant, and we'll talk about that when we get to canning and cans. And then we also have a solid food simulant. It's called MPPO, and that stands for Modified Polyphenylene Oxide. There's a trade name for it. It's called Tenax. And this is less used in the United States, although I use it quite often in my laboratory. But it's used in Europe often. It's called Food Simulant E in Europe. MPPO, I just want to mention, there's a lot of things on the California Prop 65 list that are volatile small molecules. Just a few examples: vinyl chloride monomer. EDC, ethylidene dichloride, right? What else? Styrene is another one that was added recently. Toluene, ethylbenzene. There's so many volatile compounds. What was that?
Hexane was just added.
Was it? Really? Okay. So there's so many volatile compounds. MPPO is an ideal food simulant for doing migration testing with volatile compounds like that. One thing we don't use for screening is food oil or migliol. I don't want to go into great detail why we don't do it, but we'll have questions and answers. We could discuss it. The next step is you need to figure out the food simulant to packaging surface area ratio. You could use whatever the customer intends to put in the packaging as the ratio. But default guidance with Food and Drug is 10 grams per square inch of packaging. European Union, the default guidance is 1 kilogram per 6 square decimeter square. Both of them are close. If you calculate FDA 10 grams per square inch, it is 1.57 mLs per square centimeter. The EU turns out to be 1.67 mLs per square centimeter. So they're pretty close. Then you pick the time and temperature of the extraction. The FDA has letter codes, condition of use A, B, C, D, all the way to H. J is a high temperature condition, and then microwave guidance. So we select the time and temperature of the test. So you incubate your samples, and then the next thing is you drain the cells, and we drain them into borosilicate glass test tubes or media bottles. We store them protected from light until they're ready to analyze. But you do an inspection of the extract as soon as it comes out of the cell. And you want to look for color, ink pigments, cloudiness, or precipitates, anything atypical. If there is precipitates, then often we want to characterize what that precipitate is. And we often do gravimetric determination of non-volatile residue on evaporation. And then you can take that residue and look at it by mass spec or FTIR or even NMR or other tests, and even do simple tests like is it organic or inorganic. If it's, you could put some on the tip of a spatula and burn it in a flame. If it burns, it's organic. If it leaves a residue, it's inorganic. And then we look at the substrate as well after it comes out of the cell. Is it physically distorted? Warping, shrinkage, delamination, depolymerization, ink run, and we note that as well. So here's an example of a sample that came out of a migration cell from this study. This was a can that had 3% acetic acid food simulant. And if you look at the lid of the can after extraction, this was condition of use A, which was retort condition. So it was like 121 degrees C for 2 hours, followed by 10 days at 40 C. And this is clearly a coating failure. And if you notice, the lid failed, the can liner didn't. But actually, there's two different coatings. The can ends, or the lid is different than the can body itself. So it failed. So the can's on the left, that's the substrate. On the right is the extract. If you look at the extract, it's basically got rust in it. And if you look at the sediment on the bottom, it's iron oxide. So, it's just an extreme example. So what did a cell, when we do this work, we often use migration cells. This is an illustration of migration cells that we use in our lab. I designed these cells, many years ago, over 30 years ago, different sizes. In the back, there's a 1 decimeter cell that has 1 square decimeter. The ones in the front right here are 0.5 square decimeter. Then we have different sizes. They're made out of Teflon gaskets, stainless steel plates with filling ports in the top to fill and empty the cells. The gaskets in the middle, they vary in size so that we could create any solvent volume to surface area ratio that we need. The most common is, 10 mLs per square inch. You'll see here, here's one with no filling ports. That's one that I would use for MPPO, or the solid food simulant. Since it's not a liquid, you don't have to worry about, filling it up. And then here's an odd-shaped one, a circular cell. That could be for like a can end that maybe we used in this project, or small samples. Sometimes people give us narrow web samples that don't fit in the bigger migration cells. So we have all sorts of custom cells, and we have, literally hundreds of cells and gaskets and everything to do this type of work. So how do we work up the samples for analysis? Basically, I don't want to spend a lot of time on this. We take the extracts, the liquid extracts, and we spike them with an internal standard. We use deuterated anthracene as an internal standard. We dilute all samples that are higher than 10% ethanol concentration with distilled water down to 10%. And then we do an extraction with methylene chloride. We back extract the samples into methylene chloride. And we use a fixed ratio, 40 mLs of extract and 5 mLs of methylene chloride. Then we centrifuge them with, for 2,500 RPM, 30 minutes to break the phase and make sure you get complete phase separation. Transfer the methylene chloride to tapered glass vials and evaporate on the nitrogen to reduce the volume. And in the end, we shoot for 100 times concentration. So if you start off with 40 mLs, the final volume is 0.4 mLs or 400 microliters. And you need to concentrate 100-fold if you want to get low part per billion or even sub-part per billion detection limits. Okay, so, and then finally we analyze I thought we had another one before that. No. So then we analyze the extracts, okay? GCMS, integrate the chromatograms, copy and paste the peak lists into spreadsheet templates, and then we go in and identify everything that's there based on mass spectra, but we also confirm by GC retention indices, if available, and we have a very big database. And I put here interpretation intensive, all right? The data integrity that you produce from mass spec is only as good as the libraries that you're using to identify the spectra. Libraries are limited, especially in the packaging migration arena, so you need to build your own libraries, and you have to have a big database to refer to do a really good job in this. And you often need to do interpretation and detective work to do a good job identifying the migratory species. You know, I've been at this 40 years, and we have tens of thousands of spectra in my lab, not just in packaging, but in flavors and fragrances and all different areas that we identified and created databases. And a lot of it comes from, you know, the companies that we do work for. They give us samples, we run them, we document the spectra, and we archive it, and, you know, we periodically publish a lot of this information as well. Then we calculate concentration. It's done by peak area ratio to one of the matrix spiked internal standards, and this is semi-quantitative. We assume a response factor of 1. This work right here, this protocol that I'm mentioning, it's over 30 years we've been doing it. Multiple tens of thousands of samples have been run through this protocol. The reason I was thinking about it, how long I've been doing it, all right, we started doing this before Windows, before Excel spreadsheets were invented. All right, the reason I know that is I started with database and Quattro Pro spreadsheet, building macros and reporting templates and embedding formulas and everything to do this. And it was even before we had Windows. We were using DOS computers back then. So we used to, yeah, when I first started mass spec in the 70s, we used the slide rule. We basically had an oscillograph recorder, no computer, that used UV paper etching the spectrum out, and had to take a slide rule to make the spectrum and plot it as a graph, manually, believe it or not. Yeah. So, okay. MPPO extracts. What we do with those is basically we put them into a thermal desorption tube, a portion of it, that represents a certain amount of square centimeters of packaging. And then we do a direct analysis called direct thermal desorption, GCMS. It works really well. Some people will take the MPPO and extract it with solvents like methanol or ethyl ether and then inject it. But it dilutes it, and then you have to blow the solvent off, so you may lose volatiles. When you do it one step by direct thermal desorption, we found it to be the best procedure. And then we also do LCMS on the samples, okay? GCMS is good for volatiles, but LCMS is optimized for non-volatile compounds, things that might have more aqueous solubility. I don't want to spend too much more time on it, but we go for 100 times concentration, just like GCMS, and we do it by evaporative concentration, usually in a rotary evaporator, and then redissolve the samples in mobile phase buffers that are compatible with HPLC. And it's usually water acetonitrile or 100% acetonitrile with 0.1% formic acid in it. And then we do LCMS analysis, and we do positive and negative ion mode both, because Certain compounds give strong positive ions, others are much better in positive ion than negative ion, so the data is combined and interpreted again. We also do volatile and semi-volatile outgas profiling, which is not necessarily migration testing, but can be. So I'll skip this and just show you some pictures real quick. This shows templating a sample, weighing it, seal it inside a headspace vial, and then spike it with internal standards, incubate it, and inject it into the gas chromatograph. Here's another one, purge and trap thermal desorption. You do the same thing, template the sample, put it into a glass tube, connect an adsorbent trap to it and a purge adapter to the other side, inject internal standards into the trap or into the sample. It goes in an oven, gets heated, and purged with nitrogen for about 30 minutes at 100 degrees C, and then finally thermal desorption to analyze the sample. We could also, both of those techniques, do the front, back, sides, every part of the sample. Sometimes you want to know only what comes out of the food contact surface. So we have cells that can orientate the analysis. This is doing purge and trap with a migration cell with a strip plate heater and a temperature controller connected to it. And so it's only the food side. Same thing we could do with headspace. You could put samples in here and do headspace, just put it in an oven, heat it up, and inject the sample. We just did this a little while ago. Sometimes you could, if you want, you could make a pouch out of the sample and seal it, fill it with nitrogen gas, then glue a septum to it and measure right from the pouch the same way. So let's get to the samples and what we found in the study. This is a list of the samples that were provided for analysis. On the top we have here, it was only described as reverse printed metallized BOPP, and they also said the food side was polypropylene. That's all the information that was provided. Then we have an oven board and microwave tray, which was SBS paperboard laminated to PET on both sides. Then we have can coatings, and there was 4 variables of cans and 4 variables of lids or ends, can ends. So there was 8 altogether, 8 variables of can coatings. Then we have a pouch, an aseptic pouch. This is UV ink reverse printed, and it's a flexible laminate pouch. And I have the structure of this. When we get to it, I'll describe it. And then we also have a gable top carton, which is paperboard, polyethylene extrusion coated on both surfaces, inside and out, and then externally printed with electron beam inks and varnish. So let's go to the first sample right here, substrate 1. All right, so we did food side migration testing, 10% ethanol, 95% ethanol, and solid food simulant. FDA condition of use E, which is 10 days at 40 C. This is a packaging that's used for snack food, so it's room temperature. We also did headspace and purge and trap for volatiles. All right, so I'm going to skip this. This is 10% ethanol. I'm going to go straight to the second slide, which is 95% ethanol, which is right here. So this is the results, and let me explain what we found right here. Basically, I don't know anything about this, but from looking at the data, I could tell right away it's a nitrocellulose ink system. Because nitrocellulose inks, it's very common to plasticize them with this particular blend of plasticizers. N-ethyltoluene sulfonamides, dibutyl sebacate, which is probably on the next page, sebacic acid dibutyl ester, and rosin, which when I get to the next page, you'll see the rosin. This is solvent, retained solvent from the system, which in this case is dipropylene glycol monomethyl ether, or Dowanol DPN. I just want to mention another thing. There's people talking about phthalate plasticizers, later on. These ink systems years ago used to have phthalates in them. But the companies that make the inks, they rotated the phthalates out because of consumer demand and California Prop 65 and everything else. And they replaced them with, these type plasticizers. So now these are more common. So what could we say about this? Well, the other thing is this is color-coded. So these are ink-borne migrants. Everything in white is a sealant film-borne migrant. And if you look at it, it's almost all hindered phenol antioxidant decomposition products. And if we go to the next page, down on the bottom, these antioxidants like ergophos 168, ergonox 1076, they break down in normal service, and then they give the other type of antioxidant fragments that are here, like all of these different compounds. So this is all normal sanctioned additives to sealant films that are used in food packaging. The things that are in bold are the ink migrants. And this is rosin. Rosin's very common plasticizer for nitrocellulose inks. Like rosin is mostly, this is rosin ester actually, and it's mostly methyl dehydroabiatate is like the primary components. If you look, what's noteworthy here, look at the concentration of, for instance, this plasticizer, or these isomers of plasticizers, it's over almost 200, if you sum them together, they're over 200 part per billion in the food simulant. The food industry and the packaging industry, they tend to want to keep migrants less than 50 part per billion, all right? Where does the 50 come from? Everyone in the industry has heard of Lessel-Ramsey and the Ramsey doctrine opinion of FDA going back to 1968. Even though FDA uses dietary consumption factors and dietary intake calculations, it's hard for people in the industry to run the calculations. They like a number. Give us a threshold. So unless there's anything really toxic or hazardous about the compound, we go with 50 part per billion as the cutoff. If it's a carcinogen or something, more toxic or hazardous, 100 times less, and we bring that all the way down to 0.5 part per billion. So that was the migration testing. Here's volatile, this is MPPO. It found the same compounds as, but this is what a solid food simulant would show. It's redundant. Concentrations are a little different because, a liquid solvent versus solid are going to give different concentrations. And then we have volatiles. There was not much in the way of very volatile compounds or slow solvents, except for isopropanol, small amount. But there was a lot of Dawinol DPM, which is we found in the migration test right here. And what can I say about this? You could look at this data and find a lot of information. Like, here's a compound 2,4-pentane dione. This is a decomposition product of an ink adhesion promoter that's called DuPont Tizor A. It's an organotitanate. So when you see it, you could tell that this was part of the inks. One thing to look at here is there's 3 rows of concentration, ppm, nanograms per square centimeter, and milligrams per ream. A ream is 3,000 square feet. The industry standard, not regulatory, but basically what people strive for, is to keep retained solvents less than 1,000 milligrams per ream. So here's one that's like roughly 10 times higher, all right? And there's a reason for it. This is probably a laminate, and the ink solvent gets trapped in one of the laminations, and it's really low migration on the food side, but this was measured on the total packaging. So it shows from edge extractables or whatever, relatively high. LCMS of the same sample showed the same chemistry, except for ethoxylated non-ionic surfactants and positive ion, which is very common with inks and coatings. To wet them out on the surface, they use surfactants. And negative ion showed linear alkyl benzene sulfonates, which is detergent. And a lot of samples show this, and I think it's because when they clean the presses, press cleaning solutions and stuff like that, converting equipment, you'll see small amounts of detergents. Now, how about validation? How do you go validating this? I don't want to spend a lot of time, but we have high resolution mass spec. You could do accurate mass measurement and measure the mass to the 4th decimal place right here. These are the three isomers, these peaks, 1, 2, 3, or the three isomers of N-ethyltoluene sulfonamide. Accurate mass measurement, the way it works is that every element referenced to carbon-12 has an exact mass. Hydrogen is not 1, it's 1.00 something. Oxygen has a mass defect. It's not 16, it's 15.99 something. And when you combine an elemental formula, you can only get one accurate mass for that elemental formula. So if you have that accurate mass, there's an algorithm that you could run to deconvolute it and give you the elemental formula. So, you know, this is excellent data to confirm the ID of the compound. And this is just another one of the rosin isomers, same thing, high resolution. So you want to calibrate, right, to validate as well. Here's calibration curve for one of the N-ethyltoluene sulfonamide isomers, the ortho isomer. So we have, and this is concentration of the compound, and this is the peak area ratio to the internal standard that's in there at a constant level. So it's linear. And then you could do spiking and recovery, and it shows here that for this particular compound in the ethanol matrix, which is the food simulant, the recoveries are pretty good. They range from, depending on the spike level, anywhere from 84 to 95%, which is essentially quantitative. Same thing for the other isomer, and you know, recovery for that one. He has a Dowenall DPM calibration curve for the migration testing, and spiking and recovery also pretty, you know, decent. Here's a calibration for the volatile analysis part of it done by purge and trap thermal desorption, so that you can calculate, you know, again, accurate concentrations, part of the validation. Here's data for one of the antioxidants. This is Ergonox 1076. So why would you want to measure that? Well, in the European Union in 2011, there's an SML for it, which is a specific migration limit. And they say you could use it, but the SML is like 3 to 5, I forget if it's 3 or 5 milligrams per kilogram, which is ppm, which in ppb is like 3 to 5,000 ppb. So, you know, this sample, you know, certainly had less than the SML. So, okay, it's not moving here. What's going on?
That's not me.
Okay, and again, spiking and recovery for Ergonox, good recovery in this method. All right, substrate 2, all right? This is aseptic fill pouch. This is a lamination. It was 5 micron PET, reverse printed with UV ink, adhesive, and then the sealant film inside was 1.75 mil LLD, you know, linear low density polyethylene. It's refrigerated, so condition of use F, which is 10 days at 20 C, and we did a number of food simulants. This was really, this particular sample was made for like a liquid egg product, like that you could put like egg whites or whole egg liquid in the refrigerator and decant it and use it. So this is an interesting sample. There's 3 chemistries here in the migration that are noteworthy. And they're color-coded right here. So the first one that's orange or whatever this color is right here, this is a new additive that just came out the last couple of years and I've been seeing in samples, and I had to do some detective work to figure out what it is. It's called Weston 705 Liquid Phosphate Stabilizer, and this is a replacement for what they call TNPP. Weston makes tris-nonylphenol phenylphosphate, which is a good stabilizer for polyolefins, but it breaks down and it gives off nonal phenols, which are endocrine disruptors, so people don't want them in their samples, especially infant form, you know, infant packaging and stuff like that. So they came out with this new additive, but it's proprietary, so I'll give you the structure of it. We also have UV ink and varnish. Well, I mean, that's my business, is analyzing whatever comes into the packaging. UV ink and varnish-borne migrants are color-coded. So there's acrylates, acrylate monomers, and photoinitiators. These are compounds that, when they hit with UV light, they give off free radicals and initiate polymerization. Joe Scarsello, my graduate student, has a poster on this later. You could, his research on that. So these are very common in UV cure, is acrylate chemistry. The reason being, there's really two reasons why acrylates are used all the time. Number one, when they cure, they give clear, transparent coatings. So if you want to have a varnish on the surface and see everything underneath it, or immobilize ink pigments, you don't want to have anything that covers the pigments. Second thing is fast reaction. Acrylates, when they hit with UV or electron beam, they polymerize really quickly. Even other compounds like methyl methacrylate do not polymerize as fast as acrylates do. And also there's cost, and you could make acrylates out of a lot of different precursors. So that's why they're so popular. If you look at the second page right here, you'll see more acrylates, different photoinitiators, Erga QR907, DETX, and you can go on and on. This is just different food simulants, but I'll skip right to the 95%, which is the most aggressive. At the end of the run, you see a whole bunch of peaks that correspond to this Weston 705, that new antioxidant or stabilizer. There's also slip additives like a rusamide that's in there in the film to lower the surface coefficient of friction. It's an FDA-sanctioned additive. And then we have volatiles, but the volatiles is an easy story to tell. There pretty much isn't any, because UV cure chemistry is considered a solventless system, so there really isn't much in the way of solvents. One thing I didn't note, I should go back, one other thing. There is in this sample another chemistry, which is lamination adhesive extractables. This is a laminate. It has a polyurethane lamination adhesive, which has in it polyester polyol, and this is a short chain oligomer of it. My graduate student, Alice, is giving a paper on this type of migrant, a poster session later today. So I just wanted to show the structure of the Weston TNPP. This is trisnonyl phenyl phosphate. The new replacement, they took the nonylphenols away and they replaced them with tertiary amyl phenols, a mixture of mono, di, and tri-substituted. So you get a lot of isomers when you make the phosphate out of this mixture of compounds. And you see intact material. You also see the phosphate, because these oxidize real fast, so you get an oxygen on the phosphorus. And you see the scission products, which are the tertiary amyl phenols. So I'm getting signal that I have to hurry up here. If you do have a sample that has TNPP, you'll always see nonyl phenols, and they look like this. You'll see a series of isomers. Here's a PE film that I just ran like last week that had TNPP in it, and you always see these nonyl phenols right before the internal standard comes out. And we'll skip this. This just talks about endocrine disruption, but we have an excellent presentation coming up later today about it. Beverage carton. So what did we see in the beverage carton? We'll skip right to results. This is, again, electron beam cure inks and coatings. So you don't need photoinitiators, and you see a lot of acrylates in the sample. In addition to acrylates, a little bit of photoinitiator. They seem to always be there, even though it's EB and you don't need them. If you want to know why, Greg works for an ink company. He can tell you there's always a little trace contamination in the batches that they make. Another thing here, look at this compound here, methoxychloroolefin. Anytime I analyze paperboard and paper products, and pretty much in the United States, that's a persistent organohalogen pesticide. It was banned that's the degrade date of it. It's really methoxychlor. It was banned in 2003, and for some reason, hardwood forests and what they make hardwood pulp from, it sticks to it like glue. And you'll always find it in paperboard and paper products, but really trace levels, like sub-part per billion. And according to the EPA, they say if it's under 40 part per billion, it's not an issue. And that's all. Methoxychlor is another endocrine disruptor. So we'll skip this. Again, electron beam doesn't have a lot of volatiles. So the volatile profile is really a low concentration and just, background material. Here's some validation data for acrylate oligomers. Some of them are really high recovery. Here's an ethoxylate. This is hexane diol diacrylate ethoxylated. And the higher the level of ethoxylation, like the EO units, when you get up to like 6 of them, the water solubility increases, so the partition coefficient when you do the extraction is favoring more the water-soluble phase than organic soluble, so you get a little bit less recovery. But with this, you could pick this up with LCMS, very easily. So now BPA, non-BPA food cans. We did a lot of these. I'll go right to the results on this. Here's one, interestingly, a lot of unknowns in it. These unknowns, like we did high res, so we got the elemental composition of the unknowns, and fragmentation, I could tell that they're phenolic species. So I believe they're impurities of the monomer. And their concentrations are, relatively low. But I think they go higher when you get to 95% ethanol. So let me go to 95. So here's 95%. But the interesting finding here is the monomer. This is called tetramethyl bisphenol F. This is one of the BPA replacement monomers. And also there's the epoxy of it right here, tetramethyl bisphenol F diglycidyl ether. This is a BPA replacement, supposedly not an endocrine disruptor, although I think in vitro data is showing there is something going on with it, which I guess we'll have a discussion about that later. I'm just passing this up. Volatiles, very low in cans because they're made by stoving. They spray the coating inside it, then they bake them out in an oven in a process called stoving. So you don't get much in the way of solvents, maybe a tiny trace. This shows we didn't have the spectrum of this was not in any library. So we had to interpret the spectra and, hypothesize that it was that compound. Then we bought a standard and ran it and confirmed. And this is high-res confirmation that it matches the elemental. So that's the spectrum of the new monomer. And here's the diglycidyl ether of it. Like bisphenol A has the same diglycidyl ether. It's called BADGE, B-A-D-G-E. That's bisphenol A diglycidyl ether. So this is, the equivalent from the new monomer. And these are the 2 structures right here. The trick, bisphenol A, I don't have to tell you, it is probably one of the most robust can coatings. And to get it to work with acidic food, acidic foods is the trick. And supposedly this one is, works really well. So we have another sample, SBS paperboard. And I think this is the last one, so I'll go through this really fast. One condition, which was the oven condition, they wanted 450 degrees C for 2 hours. That's really high temperature, 232 degrees C. And I'm just going to skip past microwave because it didn't show much of migrants. But when you get to the oven condition right here, you'll see everything here that I highlighted is all one chemistry. Cellulose thermal degradation products. Cellulose is a polymer of glucose, highly cross-linked. Glucose is a 6-carbon polyhydroxy compound. When you start heating it really hot, it begins to dehydrate and lose successive moles of water, one after the other. Every time you lose a mole of water, you put a double bond back in the backbone. Eventually you wind up with like hydroxy acids and things like that. Then they lactonize internally, and they start forming 5-membered rings like furanones, 6-membered rings, pyranones, and then they break all the way down to small molecules like furfural, formic acid, acetic acid, acetol. So this is the chemistry that dominated the migration in the oven boards right here. And this is all, again, cellulose thermal decomposition. Now, PET is a really good barrier. And normally you don't see many things breaking through PET, and this was pretty thick film extrusion coating or whatever it was. But at 232 degrees C, you're approaching the glass transition temperature of the PET, So it goes to the rubbery state, and then things could break through right here, like the cellulose thermal degradation. Basically, no volatiles. So again, because it's not much in the way of solvents there, did I make it? Did I meet your expectations, Greg, over here? What time?
You did great.
All right, I went a little bit over.
No, well, you started up, you did great. Thank you very much, Dr. Tom Hartman, Rutgers University, Department of Food Science, Mass Spectrometry Laboratory.